In this video, we'll work through several examples showing how we can calculate conformational energy differences between different Newman projections. So first, we're going to start with this question, which is draw each molecule in all possible staggered Newman conformations, looking down the indicated bond, as we did in the previous video. And here we're given a table of these Gauss interactions, which are the only interactions that are going to produce a difference in energy in our staggered conformations. Because as we recall, staggered is more stable than the eclipsed, and whenever we have an anti-interaction, that will contribute no additional destabilizing energy, so it won't increase the energy, in other words. So with that, here is our question. Here is our molecule that we're asked to draw. So we don't need the energy values at this stage because we simply need to draw the Newman projections first, and then we can compare what type of interactions are present in the different staggered conformations. So first, here we have our molecule, and we're asked to look down this indicated bond, and I'll label these carbons 1 and 2, and then the benzene rings, by the way, are also called phenyl, and this is how you'll see them in a typical table like this. It's abbreviated PH, and this stands for phenyl, which is the IUPAC substituent name for benzene. So this is diphenyl substituent here, and again, we'll use the molecular model to give us an idea of what we're looking at. So again, we're interested, here's our molecule. So what I did is use these blue atoms to just indicate phenyl, since they're just going to be treated as a substituent here anyway, so we're not really interested in all the carbons bound in the phenyl. So these blue atoms are both of the phenyl rings, and I'll use that as our abbreviation. So now we need to think about the possible staggered conformations that we can have here. So if we look at this, again, there's no indication if this is if the hydrogens here are out of the plane or in the plane, so there's no particular order that we need to start in. The way I'm going to do it is we have the phenols anti to each other like this, because we know that that should be the most stable. And in the second part of this question, we will show that it is in fact the most stable molecule that we have here, or conformation that we can have here. So here is our molecule. Now we just have to draw this as a Newman. So again, we start with our circles. We have this carbon in front that has a phenyl up, or a benzene ring up, a hydrogen to the left and down, and a hydrogen to the right and down. Those are these two hydrogens. Then in the back we have a phenyl, which is now anti to the other phenyl, which was the point of starting with this conformation. And then the two hydrogens are Gauss to the other hydrogens and the methyls. So this is one possible conformation. Then we can rotate about the carbon-carbon bond 120 degrees. Basically, this would interconvert a phenyl and a hydrogen while we're doing this rotation. So I'll rotate the front because I think it's the clearest. So if you rotate the front 120, that puts these phenols now Gauss to each other. Okay, so now I'll cover up our previous molecule, previous Newman, and draw this new one here, which now we have the hydrogen that's up, the hydrogen that's left and down, that's this one over here, and then a phenyl right and down. And then our back carbon stayed exactly the same. So the phenyl is still down, and then our two hydrogens are in the other two spots. Okay? And now let's imagine what else can happen here. Well, we can rotate it 120 degrees again to put the phenyl on the other spot, the other like down spot, the other left and down spot here now. So again, let's draw this. This puts the phenyl left and down here. Hydrogen is up. It's now a different hydrogen. It's not the same as the previous conformation, but it's still just up. And then the back carbon remained unchanged. Okay, so those are our three possible staggered conformations. Because now, if we rotate 120 degrees again, about this front bond. Now we're back to the anti-conformation with the phenyl and phenyl up on the carbon that's in the front and phenyl down on the carbon that is in the back. So hopefully that makes sense. Again, if you don't have a molecular kit or that doesn't make sense, the other thing you can do is draw in your hydrogens in their three dimensionality. So either out of the plane or in the plane. And then when we do exactly what we've done before in previous videos, we just rotate this out. And that is going to give us this conformation. The phenyl would be down. So I'll do one of them just doing this rotation just to illustrate that you don't necessarily need the molecular kit. So here I'm just indicating that it's a rotation, and this puts the phenyl down. So we draw our circle again. The phenyl becomes down at the front carbon now, and then this hydrogen that's out of the plane goes to the right and up, and this hydrogen that's in the plane goes left and up. And then now that puts the other phenyl up, that's in the back. This hydrogen is now here. The one that's out of the plane goes to the right, and then the one that's in the plane goes to the left. So this is exactly the same as this one because it has this one anti-interaction. It's just looking at it rotated, but it's not rotating about the bonds, the carbon-carbon bond. It's only rotating rotating the entire molecule without changing the bonds. So all of that now says that these are the only three staggered conformations. So I'll call this A, B, and C just to give us a name, a different name for each of them. Now let's figure out what types of interactions that we have. So in A, we have a phenyl hydrogen interaction, and that's all we have. We have a phenyl hydrogen interaction 4 times. Right? And we also have a hydrogen-hydrogen interaction, but that is not going to contribute to the overall energy of this. So, but we can write this all out. So these are all gauche, remember, because we're in a staggered conformation. So we have gauche interactions, phenyl hydrogen gauche. There's 4 of them. So, right, so 1, 2, 3, 4. And then a hydrogen-hydrogen gauche, there's 2. Okay, now let's look at B. We have a phenyl-phenyl gauche, which this is going to be the most significant. So I'm not going to write gauche now just to give myself more room, but hopefully it's clear that this is a gauche interaction. There's only one phenyl-phenyl interaction. And then there is 2 phenyl-hydrogen interactions, here and here. All right, so phenyl hydrogen times 2. And then the remaining are just hydrogen-hydrogen interactions, and there's 3. So I'm not going to draw the arrows for those to avoid any confusion. But there's our 6 total gauche interactions that are labeled out. And then in this last one, again, we have the phenyl-phenyl. Phenyl-phenyl times 1. And everything else is not going to contribute greatly. We have phenyl hydrogen times 2, which this might be some increase in energy, but then the hydrogens are certainly not going to have a value. So now if we notice, B and C should have the exact same energy because they have the exact same type of Gaussian interactions. We have a phenyl-phenyl interaction, and then 2 phenyl hydrogen interactions, and then just hydrogens. So those should be the exact same energy. So now we have to assess the energy of these types of interactions. So we have to go to our table, okay, all the way up here. So this tells us the approximate Gauss energy values. And how you interpret this table is you simply just look at the 2 substituents that are involved in your Gauss interaction and determine where that energy falls. So if we go back in our first molecule here, it's a phenyl hydrogen interaction. There's 4 of them. So that's what we're looking for, is a phenyl hydrogen. So you can start with the hydrogen, it doesn't matter, or the phenyl, either one. So this hydrogen, then you have to look for the phenyl on the vertical axis, so hydrogen-phenyl interaction, is 0.2 kcal per mole. So, and then again, like I was saying, you could have started with the phenyl and then look for hydrogen is this first row, so it's 0.2, and that's how you interpret this table. So now going back, our phenyl-hydrogen interaction is a 0.2 kcal interaction, and we have 4 of them, so that is 0.8 kcal. So I'm going to put above that this is all kcal per mole, so I don't have to write it because we're limited on space here, but that's our 0.8 there. Okay, then if we go all the way back up for our hydrogen-hydrogen interaction, we see that the hydrogen-hydrogen, there's a 0 energy difference. So that's here, 0 times 2 is 0. Okay, and then let's go to B and C, and we know the phenyl-hydrogen interactions because we just looked at that, and that is 0.2 per interaction. There's 2 of them, so this is 0.4 kcal per mole increase in energy, and that's the same over here, 0.4 kcal per mole. Okay, then we need to know the phenyl-phenyl. We know the hydrogen-hydrogen is 0. So now the phenyl-phenyl, going back, phenyl is 2.3. So go down here, this is 2.3, and this is 2.3. Okay, now let's add these up. So our total destabilizing energy for A is 0.8 kcal per mole. This one here is 2.7 for B. Again, kcal per mole. And same thing for C. This is 2.7. Again, kcal per mole. So what we see here is that A is clearly the most stable compound because it's more stable by 1.9 kcal per mole. So if that was unclear, I will show this a little bit more explicitly. So to calculate the differences in energy, all you do is subtract the higher energy from the lower energy. So we know that A has less destabilizing energy. So to calculate how much more stable A is than B, is than B and C in this case because they're equivalent. What you do is you take, again, this is all enthalpies, so delta H, is you take the difference, which is 2.7 is the larger value, that is B, minus the lesser value, which is A, and that gives us 1.9 kcal per mole. And the conclusion is that A is 1.9 kcal per mole more stable than B. And vice versa, B and C are 1.9 more unstable than A. All right, here we have another question. So we're asked to do the same thing, draw all 3 of the staggered conformations and then rank them in order of stability using our relative Gauss energies table. So again, first thing you want to do here is identify which hydrogens and which methyls are out of the plane and in the plane. So I'm going to say that this one is out of the plane like this. This one's in the plane. Doesn't really matter, but as long as you can see that yourself, then you're good to go. So now, once you know that, you can just rotate this out of the plane like we've done before. And I will do this with the molecular model here, but I want to start with just the rotation in your mind first this time to change it up. So when we rotate that out, it puts the phenyl group down, puts this hydrogen that's out of the plane up and to the right, this hydrogen that's in the plane up and to the left. Then we have in the back carbon, we have a T-butyl group in the back that's up. It's anti to the phenyl. And then we have a methyl group that was in the plane or was out of the plane rather, is now here. And then here is the other methyl group. So this shouldn't be a hydrogen, by the way. That was a mistake on my part. That's just a methyl CH3 there. So that is now the first conformation, and it has the T-butyl and phenyl group anti to each other. So it's most likely the most stable, even before we calculate explicitly that it is the most stable. So now we'll look at a molecular model to represent this. So again, I'm staying consistent with the fact that the blue atom is the phenyl group. So that is down in the front carbon. And now this yellow atom is the T-butyl group. And by the way, the T-butyl group is this here. It's butyl because there's 4 carbons involved, and it's T-butyl because you can draw it such that it looks like a T in the skeletal structure. So here's our first staggered conformation, and then you want to rotate it 120 degrees such that you interconvert the hydrogen with the hydrogen, the phenyl with the hydrogen, and then the hydrogen where the phenyl was. Okay, so this is our second staggered conformation, where the phenyl is now up and to the right, the hydrogen is now up and to the left, and then the new hydrogen is down, replacing where the phenyl was. And then our T-butyl has remained the same. Everything in the back is exactly the same. So T-butyl, and then the methyl and methyl. Okay, and then we rotate 120 again, gives us the third conformation like that, puts the methyl, or the phenyl rather, up and to the left, and the hydrogen, which was down, is now up and to the right, and then the new hydrogen replaces the other hydrogen in the down position, and then we have our T-butyl. Everything in the back stays unchanged. And there's the 3 staggered conformations. Because now, if we rotate again, this puts our phenyl down again, anti to the T-butyl, which is exactly the same that we started with. So we finished with the molecular model. We've identified our 3 structures. Now I'll call this conformation A, this one B, and this one C. So A, we have 2 phenyl-methyl interactions. We have Gaussian interactions again. These are all staggered. And we have 2 T-butyl hydrogen interactions, and then 2 methyl hydrogen interactions. All right. Here's our methyl hydrogens interactions. Here's the methyl phenyl. Here's the T-butyl hydrogen, and that is all 6 of them. Okay, let's move to B. So B, we have a T-butyl phenyl interaction. That is definitely going to be a very destabilizing interaction because both of those groups are so large. Okay, then we have a phenyl methyl interaction, and there's only one of those. All right, and then we have a methyl hydrogen, methyl hydrogen, methyl hydrogen. There's 3 of those. And then a methyl T-butyl, or a hydrogen T-butyl rather. Okay. For C, I'll put this over here just to separate them out a little bit. So again, we have the phenyl T-butyl. This one we expect to be extremely destabilizing because those groups are so large. There's only one of those interactions. Then we have a T-butyl hydrogen, one of those, it's this one. And then we have 3 methyl hydrogens, again, 1, 2, 3. And then a phenyl methyl. And now you notice, just like in the previous question, these conformations happen to be the same in energy because they have the exact same types of interactions. Okay, now using the table, we will see that the phenyl methyl interaction, so let me show this. So our phenyl and then methyl is the second row. Phenyl methyl is 1.4. So our phenyl methyl all the way up here is 1.4, and there's 2 of them, so that's 2.8 kcal per mole for that one. And then do we have another phenyl methyl? In C we do. 1.4 goes there. There's only 1 of them. And then in B, phenyl methyl, there's only 1 of them, so 1.4 for that one. Okay, let's go back to A. T-butyl hydrogen. So let's look at our chart. T-butyl hydrogen is a half a kcal. And there's 2 of them here, so this is 1. And then T-butyl hydrogen, there's only 1 here, so that's a half for C. And then for B, there's T-butyl hydrogen, there's only 1, so that's half. Okay, go back to the top one. So in A, methyl hydrogen is 0. So this doesn't contribute at all. So methyl hydrogen, this doesn't contribute at all. And then this last one, methyl hydrogen, doesn't contribute. So A is done. We could add A up, but let's finish all these Gaussian interactions out first. So next, the only last one is the T-butyl phenyl. And this is one that we expect to be very large. So here's phenyl. T-butyl is 3.9. It is indeed very large compared to all the other interactions that we have. So 3.9 goes here, and 3.9 goes here. Okay. Now let's add these up. So 2.8 plus 1 is 3.8 kcal per mole. Okay. And this one, this is 1.9 plus 3.9 is 5.8. Okay, and then this one should be the same. And it's 1.9 again, plus 3.9 is 5.8. So now again, what we see here, the takeaway from this is that just like we explicitly did in the previous example, you can calculate how much more stable A is than B. So what I'll do here is just write the destabilizing energy values for each conformation instead of going back and forth. So A, we know, is 3.8 kcal per mole. B is 5.8, and C is 5.8. So what this says is A, again, is now 2 kcal per mole more stable than B and C. All right, here we have a new type of question where we're again asked to draw Newman projections, but now we are asked to draw the eclipsed Newman projections, again looking down a specific bond, and we'll have to use now our table for eclipsed conformational energy changes to determine the energy of that particular conformation. And then lastly, we're asked to complete a potential energy diagram showing the change in energy between the carbon-carbon single bond rotations, which interconverts between the different types of staggered and eclipsed conformations. So here's our table, which isn't going to be relevant at this point because we first need to draw our eclipsed structures and then come back to it. So we're doing the exact same molecule that we did in the previous question for the staggered, but now we're going to do it for eclipsed. So conveniently we have our molecule already made. So again, the worst eclipsed is going to have the worst, most unstable eclipsed conformation. It's going to have the phenyl and T-butyl eclipse to each other because they are the largest groups, and if they're eclipsing each other, then they are going to have the most steric interactions that are unfavorable. So move this to the side. Here's our first conformation. So we have a phenyl up in the front, and then the 2 hydrogens down to the left and down to the right. And now our T-butyl here is eclipsing the phenyl. like that. And then we have a methyl eclipsing this hydrogen and a methyl eclipsing this hydrogen. Now again, just like we did in the previous example, we rotate this 120 to give us the new eclipse now instead of the new staggered like we did in the last question. So here gives us the new eclipsed, where our T-butyl group is eclipsing the hydrogen, and our phenyl is eclipsing the methyl there. So let's draw this. So we got our phenyl is down to the right, hydrogen is down to the left, and a hydrogen is up. And then our T-butyl is eclipsing this front hydrogen. The methyl is eclipsing this phenyl group, and then the methyl here is eclipsing the hydrogen. There we go. We get our next conformation. And then we rotate once again to put the phenyl eclipsing with the other methyl, which again is going to have the same energy because it's going to have the same interactions. So we'll draw this. We have our phenyl down to the right, a hydrogen down to the, or the phenyl's down to the left, hydrogen's down to the right, and then another hydrogen here. T-butyl is eclipsing this hydrogen now, which is different than the last one, and a methyl eclipsing this hydrogen, and a methyl eclipsing the phenyl. Okay, those are our three conformations. Now let's call this D and E and F to differentiate it from the A, B, C staggered ones that we just did earlier. So we have three interactions in each of these. In the first one, we have a phenyl T-butyl eclipsing now, only one of those, and then two methyl hydrogen eclipsing. Okay, and then in E, we have a hydrogen T-butyl eclipsing, one of those, and then a methyl hydrogen, just one of those, and a methyl phenyl, again, just one of those. And then this will be exactly the same as the last one in terms of the interactions that we have. So T-butyl hydrogen eclipsing, methyl phenyl, and a methyl hydrogen. Okay, now let's figure out what these energies are. So our phenyl T-butyl is up first in D. So a phenyl T-butyl, that is 13.5. So here you clearly see the huge difference between the eclipsed versions and the staggered conformations. So a methyl hydrogen, that's 1.4. There's two of them, so that's 2.8. So we can add that up, but we'll say that till we get them all done. So T-butyl hydrogen now, this is one we have to check. Hydrogen, T-butyl, that's 3. Methyl hydrogen we've already done, that's 1.4. And a methyl phenyl. So methyl phenyl is 1.7. Okay, and then this is the same. T-butyl hydrogen, that's 3. Methyl phenyl is 1.7. Methyl hydrogen is 1.4. Okay, now let's add these all up. This one is 1.3, so 16.8 kcal per mole. And these two, this one is 3.1 plus 3 is 6.1 and 6.1. Okay, so again, these are all kcal per mole, but I didn't show that in the value there. But now let's compare these values to each other. So now D, E, and F. So D is 16.8 kcal per mole. E is 6.1, and so is F. Okay, so now what we can say from this is that there's a huge difference here, almost 10. Again, you can do the exact same procedure we did before to know which is most stable. So E and F are almost 10 kcals per mole more stable than, or excuse me, almost 11 kcals per mole more stable than D. All right, so this is the part of the question that we need to draw the potential energy diagram. And essentially what you're showing is the difference in energy between the rotation of that carbon-carbon bond. So when you rotate 60 degrees, you interconvert between a staggered and the eclipsed structure. So, so this is like staggered, staggered, eclipsed, and so on, until you get all the way back to 360, which gets you back to the exact same molecule that you started with. So in order to show this, I think the best way is to start with wherever you want to start. So I always start at 0 with the most stable conformation, and then connect the points. So basically I'll have whatever energy is for the most stable conformation, let's say it's 4, then you go to the eclipse, maybe that's 10, then you can connect those and start to get your potential energy diagram, and then you go back to 12, this is now staggered, and so on and so forth. So if we go back to the staggered conformations, which one's the most stable, we see that it was A that has this anti that's 3.8. So we'll start here then. This is 3.8, just below the 4 there. This is A. And then we now are rotating such that A becomes an eclipsed structure. So we need to think about this, right? So if we're rotating A 60 degrees, we're putting methyl, we're eclipsing with the phenyl rather eclipsing with the methyl, and the hydrogen eclipsing with the butyl. So when we go to the eclipsed, we need to see what the energy is for that option. So we're looking for a phenyl eclipsing with a methyl and a hydrogen with a T-butyl. So that is this one. So this, since there's no difference between E and F, you can pick which one you want to be here, but we're going up to 6.1. So that's here, and this is E or F, like I just mentioned, it's either one. Then now you rotate again such that you're back to a staggered conformation, and now you are you're rotating from E, so you're putting it so the phenyl and T-butyl are gauche to each other. So you need to look for the staggered conformation, which is that. So phenyl T-butyl, that is C here. So this is C, and we know C is 5.8. If you look at the what I just passed through, the table just passed through, that's 5.8. Okay, and now 180 again, this puts us back to an eclipsed, but now we're rotating from C, so 60 again puts us eclipsing with the T-butyl group. So that is our most unstable, that's here, it's D, and D is 16.8. So this table doesn't allow me to go that high, but let's say it's, it's very high above our list, so somewhere like there. That was D, right? Then we rotate 60 degrees again, such that we get staggered here, where the phenyl is now adjacent, or gauche rather, to the T-butyl. So that's this position, that's B, and B is 5.8. So we're all the way back down to 5.8, which is like here. And then 300 gives us our last. Again, we're rotating from this one to put the phenyl methyl eclipsing each other, which is D at 6.1. So here, and then D is just above 6, so it's like here. And this was F. Yeah, so this was F. And then when we rotate to 360, it puts us back at 4. This is essentially A repeat of A. So now to finish the diagram, all you do is connect these dots, and you try to do it gradually, because this energy is going to gradually increase as you're increasing the interactions the closer these get to eclipsed. So this kind of goes like like this. This, there's going to be basically no difference. And this one's going to slowly increase all the way up to the eclipsed with the methyl or the phenyl and the T-butyl. And then this is going to fall back down to the staggered. And then there's an increase in energy back to an eclipsed. And then we go back down to our original most stable. So this is how you would assess this type of question. So again, what you should notice is that we have these positions that are exactly the same in energy, and that was due to the symmetry of this molecule that we looked at. But they could be different, such that all of these staggered and eclipsed are unique in their energy, but it's not the case here. So anyway, that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a question or suggestion, please feel free to leave it in the comment section below, and I'll get to it as soon as I can. So with that, I hope you all have a great day, and I'll see you in the next video.